Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore the fascinating world of robot anatomy and motion. On this first slide, you'll see the title, Robot Anatomy and Motion, along with a brief overview of what we'll cover. We'll be looking into the physical structure of robots, their motion systems, and the degrees of freedom that allow them to perform complex tasks. Over the next few slides, we'll dive into each of these areas in detail. So let's get started. Today, we're focusing on some key learning objectives that will deepen our understanding of robotic systems. First, we'll explore various types of motion, joints, and links, which are fundamental to how robots move and function. Understanding these components helps us see how different configurations enable different tasks. Next, we'll look at how links and joints combine to create specific movements. This is essentially how robots translate their design into action. Finally, we'll discuss the concept of degrees of freedom, or DOF, and how this impacts what a robot can do. Grasping DOF is crucial because it defines the potential and versatility of robotic systems. Throughout this session, keep in mind that these concepts are interconnected. They all contribute to building more effective and adaptable robots. So, what exactly is robot anatomy? Well, it refers to the physical structure of a robot, the actual components that make it up, and how they connect and work together. Think of it a bit like a living organism. Just as our bodies support our functions and performance, a robot's anatomy is designed to do the same for its tasks. Key components include sensors, which help the robot perceive its environment, actuators and motors that enable movement, power sources that keep everything running, and computing units that process information and make decisions. All these parts are carefully arranged to allow the robot to move, interact with its surroundings, and perform specific tasks effectively. Understanding this anatomy is really essential because it helps us design robots that are not only efficient and durable, but also easier to maintain and upgrade over time. When we grasp how each part works and connects, we can create robots that are more reliable and adaptable, fitting seamlessly into the overall theme of building smarter, more capable machines. Let's take a closer look at the motion planning process. First, we need to define the task. This means understanding what goals we want the robot to achieve, as well as any constraints or specific requirements that will influence its movement. Clear task definition sets the foundation for everything that follows. Next, we determine the workspace. This involves establishing the physical boundaries and operational areas where the robot will be working. Knowing these limits is crucial to ensure safe and efficient operation. Then we define the kinematics. Here, we're looking at the robot's joints, links, and degrees of freedom. Basically, understanding how each part moves and how they work together to achieve desired positions. After that, we generate the motion plan. This step uses specialized algorithms to plan paths and trajectories, ensuring movements are smooth, efficient, and collision-free. Finally, we validate and implement the plan. We test it first in simulation to catch any issues, then deploy it on the actual robot system, making sure everything works as intended. And of course, the process doesn't end there. We continuously monitor the robot during operation and make adjustments as needed to optimize performance and respond to any unexpected conditions. This iterative approach helps keep the robot operating safely and efficiently within its environment. Now, let's take a closer look at the different types of motion we see in robotics. First, we have linear motion, which is essentially straight-line movement. This is commonly achieved using motors, actuators, or hydraulic cylinders, and it's fundamental for tasks like moving an arm forward or sliding a component along a track. Next, there's rotary motion, which involves rotation around an axis. This is typically powered by motors or servos and is essential for joint movements, such as turning a robot's shoulder or wrist. Rotary motion gives robots the flexibility to position tools or sensors precisely. Then we have oscillatory motion, which is back-and-forth movement. This kind of motion is often generated using motors or piezoelectric actuators. Think of applications like scanning sensors or robotic arms performing repetitive tasks, Oscillatory motion makes that possible. Finally, there's flexure motion, which is quite interesting. It involves movement through the elastic deformation of flexible materials, like springs or flexible beams. This allows for smooth, precise adjustments without traditional joints, and it's particularly useful in delicate or high-precision tasks. Understanding these different motion types helps us grasp how robots can perform a wide range of tasks efficiently and reliably, which ties directly into designing versatile and effective robotic systems. Understanding joints is really fundamental to grasping how machines and biological systems move and function. So why do joints matter? Well, they are the key to enabling movement. They allow us or machines to rotate, bend, and slide in multiple directions, which is essential for flexibility and adaptability. Next, joints are crucial for precision. They give us accurate control, especially when performing delicate tasks where even tiny movements matter. This precision is what makes complex operations possible, whether in robotics or in our own bodies. Additionally, joints provide strength. They support heavy loads, particularly in challenging environments where the forces involved are significant. Without strong joints, it would be difficult to handle the demands placed on our systems. And finally, joints contribute greatly to longevity. By reducing wear and tear on components, they help machines and biological systems last longer and operate more reliably over time. Connecting all these points back to our overall theme, understanding how joints work helps us design better, more efficient, and more durable systems. Whether we're talking about robotics, prosthetics, or even biological health. Let's take a closer look at some common joint types used in robotics. First up is the revolute joint. This type of joint rotates around a fixed axis, similar to a door hinge. It usually has a range of about 180 degrees, allowing for smooth and controlled rotational movement. Next, we have the prismatic joint, which provides linear sliding motion. This is perfect for tasks like lifting or lowering objects, where straight-line movement is essential. Then there's the cylindrical joint, which combines both prismatic and revolute movements. This allows for more complex, multi-directional motions, making it very versatile in robotic design. Moving on, the ball and socket joint offers multi-axis rotation, much like a human hip or shoulder joint. This type provides a wide range of movement and flexibility, crucial for more sophisticated applications. Finally, we have flexure joints, which are quite innovative. They use the flexibility of materials themselves to achieve precise micro-robot movements. This approach is especially useful in delicate tasks requiring high accuracy. All these joint types play a vital role in enabling robots to perform a variety of tasks, connecting back to our overall theme of creating versatile, capable robotic systems. Let's take a closer look at some common robot configurations. First up is the Cartesian robot. Like the FANUC M20IA, this type moves linearly along the X, Y, and Z axes, making it perfect for pick-and-place tasks. It can handle a payload of 20 kilograms and has a reach of about 1,717 millimeters. Its straightforward movement simplifies programming and precision, especially in repetitive tasks. Next, we have the jointed arm, exemplified by the ABB IRB 120. This configuration features multiple rotary segments, giving it a lot of flexibility and dexterity. It's well suited for assembly and material handling, with a payload capacity of around 3 kilograms and a reach of 580 millimeters. This design allows for complex movements and better maneuverability in tight spaces. Then there's the SCARA robot, like the Epson LS3. The SCARA is designed primarily for high-speed assembly on a horizontal plane. It can handle up to 3 kilograms and has a reach of 400 millimeters. Its structure allows for rapid, precise movements, making it ideal for electronics manufacturing and other high-volume, fast-paced applications. Finally, we have the cylindrical configuration, such as the Kawasaki RS010, and this type combines rotational and linear motions, giving it a versatile range of movement. It can carry up to 10 kilograms and reach out to 1,400 millimeters. This setup is often used in machining and welding, where both precise positioning and strong payload capacity are important. Understanding these different configurations helps us choose the right robot for each specific task, ensuring efficiency and effectiveness across various manufacturing processes. Let's take a closer look at degrees of freedom, or DOF, in robotic systems. Typically, when we talk about 6 degrees of freedom, we're referring to the ways a robot can move in space. These are divided into translation and rotation. For translation, think of the robot moving in space along 3 axes: heaving, which is up and down, surging, which is forward and backward, and swaying, moving side to side. These movements allow the robot to position itself precisely in 3D space. On the rotation side, we have pitching, which tilts the end effector forward or backward, yawing, which swivels it left or right, and rolling, which pivots it side to side. Together, these rotational movements give the robot full control over its orientation. Most industrial robots are designed with 5 or 6 degrees of freedom. 3 are dedicated to positioning the robot in 3-dimensional space, X, Y, and Z axes. The remaining 2 or 3 control the orientation of the end effector, giving the robot the flexibility it needs to perform complex tasks. Understanding these degrees of freedom is fundamental because they define how versatile and precise a robot can be in its environment. This concept ties back to the overall theme of robot design and capability, highlighting why the number and type of DOF are so critical in robotics applications. Let's talk about the capabilities and trade-offs of different DOF, or degrees of freedom, robotic arms. Starting with the 3 DOF arms, these are typically used for basic tasks like welding or simple pick-and-place operations. They are straightforward and effective for specific, limited functions. Moving up to the 6 DOF arms, these provide full 3D positioning and orientation control, meaning they can reach complex positions and angles with much greater precision. And then we have the 8 DOF arms, which offer maximum flexibility. They have the highest range of motion, allowing for more complex tasks and better maneuverability. Now let's look at the benefits. With more DOF, you get greater versatility across multiple tasks, increased strength and payload capacity, and enhanced flexibility, speed, and precision. Plus, you can operate over a larger range without needing to reposition the arm constantly, which saves time and increases efficiency. But of course, there are trade-offs. More DOF means more potential failure points, which can require more maintenance. Complex operations also demand trained technicians to keep things running smoothly. And naturally, the initial setup and ongoing operational costs are higher. Additionally, if a single joint fails, it can impact the entire system's functionality, which is something to keep in mind when considering these systems for your operations. Ultimately, choosing the right DOF depends on balancing these benefits and limitations to meet your specific needs.